Okay, so welcome everyone. Thanks Masha for the introduction and also for the invitation. Same thanks go to Nived and Federico. It's my pleasure to be here, and I hope I will be able to entertain you here for the next 20 minutes. I want to talk about robotics and phenotyping for sustainable crop production. I kind of want to set the frame a bit why that is relevant and start maybe 4 or 5 more minutes than regular on why I think this is an important problem, and maybe that also sets the frame or the motivation for some of the interesting talks that are announced for this workshop and for the remaining part of that day. So first of all, the most important question always is why? Why should you care? Why are you here? Why are you attending? And maybe you're attending because your supervisor told you, hey, there's a workshop that looks interesting, please go there. Maybe you're here based on your own interest, your own internal curiosity. But I want to set the frame a bit broader and introduce why I believe agricultural robotics is something relevant to consider. And I want to start with one plot which I very often or frequently use for the introductions of talks in this area. And this basically shows the world population, how it is evolving, and there have been made calculations how much biomass we actually need to produce in order to have enough biomass for our everyday life the way we live today. And if you look to the amount of biomass that we need to produce from 2010 to 2050, so within 40 years, this is approximately the same amount that we have produced from the beginning of mankind until 2010. And this is obviously a substantial amount, and we need to do this within just 40 years, of which 10 years already have passed. And the additional challenge here is not just to produce it, but to produce it in a sustainable manner, so that also life after 2050 will be good, and the subsequent generations have the chance to live the life they want to live. And so the question is, why do we need so much biomass? What is driving biomass up? And there are a lot of things which are out there. If you look into the increased production of biofuel that we use to put gas into our cars, then this has been a 100% increase in the last decade, which is quite substantial, and it doesn't look as if this number is going to go down in the future. The other thing which drives crop production or the demand for a higher yield up, and this is the increased meat consumption. So if we look into the increase in meat consumption worldwide, we can see there has been a substantial increase, and there's forecasted a 45% increase until 2050. And you may say 45%, maybe that's not that bad. But if you look to the amount of calories that you're producing with meat, it actually turns out that you need between 7 and 10 times more land per calorie if you eat meat compared to the case if you would eat the crop directly, because the cow needs to eat the crop and then we are eating the cow. And that's kind of suboptimal from the point of view of calorie use. In addition to this, we are using a substantial amount of agrochemicals today. And this has negative impacts on our agro-ecosystem. So if you look at some of the statistics looking over the last approximately 30 years, we can see that even the protected areas in Germany, we lost around 75% of the biomass of flying insects, which is really substantial. And so there's not just a demand for a higher yield. At the same point in time, we also need to make sure that we protect our agro-ecosystem. So if we summarize the main challenges in crop production today, we can see that on the one hand side, we have a demand for a higher yield, especially if you see it from a global perspective. At the same point in time, we have limited arable land, so we cannot simply increase the arable land and say, let's use 3 times more arable land. That's simply not available. At the same point in time, we are using a massive amount of agrochemicals these days, for example, herbicides, in order to control weed growth or to perform plant protection, which has in part negative side effects on our agro-ecosystem. And also climate change adds a substantial amount of uncertainty. So it depends where you live, what the impact of climate change on crop production is, but for sure it increases uncertainty, and certain processes simply run faster. So it's harder for the breeding companies, for example, to adapt crops to fast climate change because the changes are so quick. So we can sum all this up into one question that we should tackle. And this is also the question that we in Bonn have as our leading questions towards the research I'm presenting here. The question is how to reduce the negative impact of crop production on our ecosystems and at the same point in time address the demand for a higher yield and make sure we don't compromise the yield by reducing the negative impact on the agro-ecosystem because there's dependency between them. And so the question is, how can we achieve this? What are the levers we have in our hands in order to control that? And there are basically two main things we can do for increasing yields, and as it will turn out, also for reducing the negative impact on the agro-ecosystem. So if we look to the yield, we have kind of our potential yield and our actual yield. So actual yield is what we're actually producing today, and the potential yield if everything would be kind of in perfect conditions without plant diseases, for example. And there are kind of two levers we have in our hand that we can use in order to kind of push up the expected yield or the yields. And these are improved management capabilities, so means operating on the field, what kind of things we are actually doing on the field. And the second thing is breeding. So being able to support breeders to more quickly adapt to climate change, to breed crops which are more resistant with respect to certain diseases, for example. So by improved breeding and improved management, we can actually push up the yield. And if you look on the other side, what are things that have an impact on our agro-ecosystem? And one of the impact are the inputs that we are generating. It doesn't cover everything, but it has a substantial impact on several different aspects. And so the thing is, if we can actually bring down the amount of inputs, such as whatever herbicides, fertilizers that we input into the agro-ecosystem, then we can also reduce the negative impact. And also breeding and management are two levers we have in our hands in order to control that. So, for example, by performing management actions not specific for a field, but specific for every plant, if you can do this in automated fashion, then this can reduce the amount of agrochemicals that we need, especially in weeding applications, for example. But also, if we provide better information to the breeders, they can speed up the breeding processes and optimize for a reduced amount of fertilizer, for example. Okay, and so these are within PhenoRob, which is kind of the cluster of excellence that we are heading here in Bonn around this topic. It tries to address these challenges by having kind of 4 research units in which we are conducting research toward this joint mission. And the first one looks in developing digital technologies. And this is kind of the area that is probably closely related to you, to this audience here today. And therefore, I will focus in my talk on this part. And here we're looking into developing new digital technologies from UAVs, from ground vehicles, machine learning algorithm for interpreting the data, deriving relevant information that we can see from the sensors about the environment. But then besides this, we are also looking into getting a better understanding of the plant, the soil, and the interaction between soil and roots, for example. And this is a large amount which looks into different phenotyping activities related to individual crops, related to roots, monitoring our soils, making sure our soils will be able to sustain in the long run, and also the integration of this technology into the environment, monitoring larger areas, also into economic aspects, because new technologies will only be adapted if we are actually able to make this economically interesting for the farmer. Otherwise, the probability that things happens is substantially reduced. So I want to now, as this is a workshop on agricultural robotics, focus on the first part of this talk and start with the question how robotic monitoring and intervention can help us towards a sustainable crop production. And I said again, I think these 2 levers, improved management and improved breeding. And for that, we need often to assess the state of an individual plant. So how is the state of the art in plant assessment? And this is often done by manual inspection. If we are in greenhouses, we may have facilities where we bring the individual crops into a phenotyping facility, into a sensing system where plants in pots are brought there, scanned, for example. But if we're operating on the field, and the conditions in the field and in the greenhouse are typically still quite different, then this is often done by hand. And if you look into weed control as one example for management actions, we can see that either there is the traditional conventional way of spraying the whole field, or there are other things in organic weeding where this is basically done by manual work. And here, one of the questions that we of course have, can robotic technology help us to do that in a better way? We're not spraying the whole field, but not requiring manual work in order to do these tasks. And as you can imagine, I see several ways of how this can be done. And if you look to the two tasks that are out there that I mentioned, which is monitoring and intervention, then we can see that these are two key tasks that we need to address. And kind of monitoring, you can actually refer to as knowing what's going on the field, and intervention as kind of doing the right thing. So you need to assess the state and then make a decision on what to do. And I will start with monitoring and then look into intervention and give you some of the examples how we are using technology and new developments, and where maybe see also challenges for these individual tasks. And a lot of the activities and talks that you will actually see in the remaining part of the day focus on aspects of monitoring, intervention, harvesting, different activities that happen on the field. So the easiest form of monitoring, or the most simple one, is probably using a UAV. We're using UAVs. These are fairly simple platforms which are comparably cheap because they have been used for a lot of other tasks, not only just for crop monitoring, or even crop monitoring is probably not at all the main target for DJI, for example, promoting their Phantom drones, which is one of those which you can see over here, which you can use to make nice, whatever, YouTube videos if you fly over areas, but we can also use them for crop monitoring. So the drone has a downward facing camera, you can see over here, and you can observe, where in this example, the sugar beet fields on the ground, and we can actually interpret this image data. We can do this for UAVs, or we can do this for UGVs as well. So that's not restricted to one of the platforms. And what we typically want to do is we want to take an image and interpret what we see in that image. So we want to, for example, label every pixel in that image into saying, okay, this is the crop I'm interested in, here my sugar beet plant, or it is a wheat shown here in red. And there will be some computer algorithm running in the middle, probably a learning-based approach these days, that will turn this image into this semantically segmented image. And if we have that and stick all those images together, we can actually generate basically a map of our field and analyze that field and saying, okay, in certain areas there is a high weed pressure, in other areas everything looks fine, or in another area there's a slow growth, so we may need to add some fertilization, at least locally. And a lot of activities and research that we're doing is actually how to make that interpretation. And if you start that today, you will probably start taking out one of the standard semantic segmentation systems that are based on CNNs, convolutional neural networks, where you have as an input your image data, your camera images from your drone, and this system turns it into a semantic segmentation mask, basically an image where every pixel providing a color stands for a certain semantic class. And that's something that we have done in robotics also for quite a while, in autonomous driving, in human-robot interaction applications, into mapping and SLAM systems that we have built, but we're using this semantic information in order to analyze the field. So we can see here, for example, in the first row, how the input image is turned into an image where you see different colors referring to whatever vehicles, ground, pedestrians, sidewalks, vegetation, things like this, or you have systems which in green just identify people. Over here is actually see Yvette over here, so that's Yvette, a picture from the Christmas market in Bonn while he was living in Bonn, and other systems which where you try to filter out the humans that you see in your scenes. And within my group, we have put quite some efforts into building those semantic segmentation systems that run in real time and provide you with a pixel-wise segmentation of different semantic classes, so that we can actually run this online on our field robots. And if you do this, you unfortunately have the issue in the agricultural domain that you typically have a limited amount of training data available. So there are less images of whatever sugar beet plants out there labeled than human faces. And therefore, there is a smaller amount of data that you can use to train your learning algorithms. So we are putting quite a bit of effort into the question on how we can actually leverage background knowledge about the domain we are operating in order to boost up learning so that our algorithms can run with a small amount of training data. This could be unsupervised approaches, but this could also be systems where we are adding additional input information into the system, exploiting information that we have learned from the old days of supervised classification, which features are useful to make certain decisions, to help the neural networks to not learn everything from scratch, but to have a good starting point. And in this way, reduce the amount of training data that we need, maybe by a factor of 10 or maybe even by a factor of 20 or 30, and still get good classification results. So that's something that we are focusing in research-wise here in this area. Then we can use those networks for different types of applications, for interpreting, for example, doing crop weed classification, for identifying berries if we are doing pruning tasks in vineyards, or yield estimation in vineyards, so we can use it for different applications in the agricultural domain. And again, we can also commercialize it more and going towards supporting breeders. So if you take a more expensive drone with a really high resolution camera today, you can actually fly with even small drones over larger fields. For example, having a 5-hectare field, and you can actually zoom in into these fields up to a fairly high resolution. This is 2mm ground sampling distance, this example, and then you can run different analysis, not just the simple segmentation on those systems. So what we can do today is we can do things like weed mapping, we can do breeding plot analysis, we can perform ear counting in weeds in order to have a yield estimate. We can look into homogeneity of different plants to support breeders, emergence counting. So there are a lot of analysis which we actually can do on a fairly automated fashion today, or completely automated fashion today, and which is actually ready to be used in applications today. And it's also starts to be commercially available. So besides the task of knowing what's going on, we also need to do the right thing. So I want to shift the focus a bit from monitoring to interventions. So if we say we have now that system where we can turn the image into a semantically segmented image, then the next step is, okay, how can we, for example, perform an action so that the weed gets eliminated? So how can we actually kill the weed in this example? But this could also be other actions if I'm not looking into the weeding application, but into other management actions in order to perform an action to change the current status of the field. And so what we can do, we can put these systems on mobile platforms, ground vehicles that drive over the field. This stems here from a project Flourish, at that time coordinated by Roland Siegwart at ETH Zurich, actually a point in time where Masha was a PhD student, and she also worked on that project here a couple of years back. And we have been building semantic segmentation systems that we can run on those robots, and so that the robots, are then on the field, can actually perform intervention actions. And so this is an example of a system built by Bosch within this project, which is basically a stamping system. Let's call it a glorified Bosch nail gun, which you can drive over the field and stamp small weeds back into the ground. That's a system which worked fairly well for small plants, but has its limitations as the wheat plants get larger, and also the durability of this system has space for improvement. So there's probably not this final system that you will find out in the field. So more likely will be a selective spraying system at the first step, and then looking into other techniques for weed removal, for example, free of chemicals. And for that, you need to inspect the fields also a bit further. I'm sorry, stepping a bit further in the interest of time, so that certain weeds, for example, have to be sprayed, like grass weeds, or cannot easily be stemmed. Others you want to stem, and you can also adapt the learning algorithm that they don't just provide you with the semantic segmentation, but also then really trigger the treatment that needs to be done, and also select the proper treatment for the individual plants. And you can even take that a step further and do laser-based weed control. So there's another startup out of the cluster, Escada Technologies, which looks into using other things like a laser to burn away the weed and do chemical-free weeding. So this was one of the first experiments. By today, we can do this in a couple of milliseconds and don't need that long treatment times. And there are still a lot of challenges out there if we want to do this in robust fashion. And one of the things is generalization performance. So if we train classifiers, for example, here in this project in our fields in Bonn, and then move to another field in Zurich or in Stuttgart, then the field A and the field B will look different, and this will lead to a reduced performance of these classification systems. So those classification systems really work well if they are operating the same domain. So that means if the images from the the training data and also for my target domain or source and target domain are actually similar. If this is my source domain and my target domain, however, looks like this, so the images look substantially different, then those classification systems typically will perform fairly badly. And a couple of efforts go into this. How can we actually translate the data that we have so that the images from both domains look similar, or we have a similar performance? And this is something that is called domain adaptation, which we are also doing research on, where Federico, for example, is working on trying to change the system in a way that we get training data also for, or we can translate the images between target and source domain so that we can make the target images look like in the source domain or the other way around, and this way improve our systems. And there are several practical challenges out there, from using different cameras, using different robots, operating on ground vehicles, aerial vehicles, into different soil conditions. So there's still a lot of challenges that need to be addressed in order to make this system operational. I will skip over my remaining slides and actually come to an end. So where I see that we are right now in weeding really far. The next steps are fertilization, maybe irrigation tasks, as well as crop production with an increasing complexity. And something I haven't covered at all, but I've with interest seen that also harvesting will play a role in this workshop. You can see harvesting as an intervention action, but I would actually decouple it a bit and see this one of the next big challenges, especially if we go into special areas such as mixed cropping or patch cropping experiments, where we can try or use mobile robots to try completely new field designs, but then a lot of challenging questions arise in this domain. So with this, I'm coming to the end. I thank you very much for your attention here. I hope I've set the frame a little bit for the workshop that is coming today and showed you a couple of applications where we have worked, which I think are interesting, but I really don't want to exclude the harvesting part. It's just that I have a much smaller background on that, but I think it's one of the key challenges that we also need to address to have the full pipeline actually covered in here. For a lot of the problems, it's not enough to just work on the robotics part. You need to team up with someone with agricultural experience, and actually being able to talk to each other and do work jointly is a key thing. But it will allow us to tackle a lot of challenges that our society is struggling from. So I think it's something which will be very rewarding. With this, I'm actually stopping here and would like to open the stage for questions, for discussions, and have a lot of interactions with you. Thank you very much for your attention.